Hey you guys, in the previous video we took a look at the linear search algorithm, and while that does have its benefits, here we're going to take a look at binary search. So what's the big difference between binary search and linear search? There are two main differences. The first difference is the assumption of the data that we are working with. With linear search, we are assuming that the array is random, or there's some sort of pattern in which we don't know the order of what the data is going to be in, right? And that's for linear search. For binary search, there is an assumption. The assumption is that the array that we're working with is either sorted from low to high or from high to low. The other difference between binary search and linear search is that linear search has a linear runtime, meaning in a worst case scenario, if we have an array of length 10, it'll take us 10 searches to find out whether or not we have a successful search or not. However, with binary search, it's going to be the logarithm base 2 of that array. So because it's a logarithmic function, this algorithm actually scales better than linear search. And that is because logarithmic functions, they grow slower than linear functions. And in a nutshell, what that means, the more n grows, well, if it's a linear runtime, it's going to grow with n. However, if it's logarithmic, it's going to be log n, which is a greatly reduced value of n. N grows normally, linearly, with n as it increases, but log n increases much more slowly as the number of n grows. So the bigger the array, the amount of comparisons that we will need to compare it using binary search grows very slowly. Anyways, with that out of the way, let's take a look at my main here. So I have a vector of integers, 7 to be exact, and they're sorted from low to high. I have two search queries, which is search 1, which has a value of 20, and search 2, which has a value of 21. And actually, just to change it up, just to go a little bit higher, I'm going to have a search value that's 25. And these are going to be the two items that I'm going to use to search my vector x. But instead of using something like linear search, I'm going to use binary search. So let's start with the implementation of the algorithm. Since I want it to be generic, I'm going to make it a template, and like the first version of linear search, I'm going to have my binary search that's just going to return whether the item is inside of the array or not. I have my vector, which I made it a const because I'm only accessing the values. I'm only interested in accessing the values and not writing to it, right? I don't want to change any values of v because I'm just searching it, and I have my t value, which will search the array. So how binary search works is that we get the bounds of the entire array. So we need a beginning, which will be equal to 0 because that's the beginning of the array, because all arrays begin at 0. And then I'm going to have my end, which is going to be the size of my array minus 1. I'm using vector and array interchangeably, so if I say array, I also mean vector. But now that I have my bounds set up, the beginning of end, in this case right now in these first two lines, the beginning and end at this point covers the whole entire array. So what I'm going to do is I'm actually going to create a infinite while loop. And this kind of seems counterintuitive because you have an infinite loop. Like, having a loop like this makes you think that, man, this is going to go on forever or for a really long time. And it's a little bit counterintuitive because this algorithm runs for a really short time, but having this infinite while loop kind of gives them the impression that it won't. Anyways, moving on. So how binary search works is that it searches at the middle of the array. And if it's not our value, we actually divide our array into two halves, and then we go either to the right half or the left half. We look in the middle again. If it's not equal to our value, we turn our remaining array into another left half and right half array. So we go into the either right half or left half array, search in the middle again, and we keep repeating that process. In order for me to search at the middle of the array, I need to have my middle index, which will be the sum of begin and end, and I need to divide it by 2. And actually I'm going to put a parentheses here so that way I'm explicit with my division. So the first thing that I'm going to check is that if our vector v mid is equal to the value. Because how this algorithm works is that the actual searching is in the middle of our array that we create. If our value is equal to vmid, we are going to return true. Next, what I'm going to do is that I'm going to update my mid. So if it wasn't found in the middle of the array, what I need to do is I need to section off my right half and left half subarrays. So I do that by first checking if v of mid is greater than the value that I'm looking for. If it turns out value is less than the array that the element that I just accessed, meaning the middle of the array, I'm going to have my end equal to mid plus 1. Sorry, minus 1. Otherwise, the other case is that our value is greater than vmid, so then I'll have beginning equal to mid plus 1. And notice how we're not reusing mid again. And we don't need to, because when it comes to it, we've already searched that mid. Once we searched it, we don't need it anymore. So I've checked, my first if statement is to check if my value is equal to what I'm looking for. If it is, I return true and everything's good. The middle if else statement updates my indices that I'm going to be continuing to search in my next iteration of my infinite while loop. And here I'm going to create my exit condition. So here I'm going to say if begin is equal to mid or end is equal to mid, then we're going to return false. Because what this means is that we've gotten so far either to the far right or to the far left that we're searching, well, in this case, if we have our vector x, we have searched 2 and we have searched 22, and that's our left or right subarray. And if that's the case, well, it's like, oh shoot, well, we're out of elements. If I've searched that one element and it's not there, well, we're done. So here I'm going to terminate my while loop, and just to quiet my compiler, I'm going to return false. So why do I do this? Some compilers actually give warnings and sometimes even give errors if you have your return statements only inside of a loop and don't have something outside of a loop, just in case it breaks out. So I usually like to add a default, a safe thing to say, and say just return false. With that being said, let's work on our tests so that way we can check that our binary search works. I'm gonna have a function called for search 1 and for search 2. Here we have it. We have our binary search. So x was search 1. This should return true because search 1, which has a value of 20, is inside of our array x because it's right here. However, the second binary search will return a 0 because 25 is not inside of our vector x. So let's see it come to life. Oh, I made a common error here. So instead of having double equals to compare it, I have a single equals. Subtle but very important difference. So let's compile again. I have no errors. I do that. 0 and 1. This works perfectly. This is great. So real quickly, now that we have our algorithm implemented, I want to quickly give you guys an example to compare linear search with binary search. Let's say I was searching for the value 22. If this was linear search, I need to search from the beginning of the array all the way to the end. So it'd take me a total of 7 searches to get 22. If this is binary search, what would happen is that I'd check 12 because it's the middle of the array, and then I'd move on to 20 because that's the middle of these 3, and if it's not there, I move on to 22. So that's 3 comparisons compared to 7 with linear search. However, there's a drawback to that, right? If I wanted to search for my value 2, linear search, I'd only have to do 1 search, which is pretty good. However, with binary search is going to be another 3. And in the worst case scenario, if I have my value 25, it's going to take me 3 searches to determine that it's not there. But linear search is going to take me all 7. And that's the kind of things we got to consider when we have the runtime of these algorithms. But however, since binary search needs to be sorted first, there's kind of a drawback, right? It needs to be a sorted array before you can search it. But you have this gain in search efficiency that it might be worthwhile to have, a vector sorted. But that kind of brings me to another question. If I have a random array and I'm going to be searching a lot of it, and it's not sorted, it's probably not a good idea to use linear search. It might be a good idea to find a way to sort it and then use binary search to search for it. But how would you go about sorting that array? Well, in the next video, I'm going to introduce you to another algorithm called insertion sort, and I'll see you there.